we want to figure out where the line y is equal to 5 minus 2x is closest to the origin. So if you think about this, you have a y-intercept of 5 and then a negative slope. And so the question that they're asking here is where on this line, y is equal to 5 minus 2x, is the distance between this line and the origin the smallest. So what we are trying to do here is we are trying to minimize the distance between the line and 0, 0. And the constraint here is subject to the fact that we are talking about this very particular line, y is equal to 5 minus 2x. All right, so in order to minimize this distance, to get where this line is closest, so where the distance is smallest, we have to refer back to our distance formula. And our distance formula, remember, is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And that comes directly from our Pythagorean theorem and using the legs for x and the leg for y. So in this case, what I'm going to do is I'm going to say that we're trying to minimize the distance. So the distance here will be the square root. Now, one of our points will just be x, and the other point, so again, to really emphasize this, when you look at this line here, the point that we are trying to find is x comma y. And then the other point that we have is going to be 0, 0. Okay, so we have x minus 0, that would be the difference in my two x coordinates, plus, and then the difference in my two y coordinates would be y minus the y coordinate of 0. Okay, now it is subject to the constraint that y is equal to 5 minus 2x. So what I'm going to do is I'm going to plug in that constraint. Now, of course, this just becomes x squared plus, and then here our y is 5 minus 2x quantity squared is equal to our distance. All right, now this next part is a very important little side note about this. But if you think about it, minimizing the distance is the same problem as if I were to minimize the distance squared. Now, the reason why this is helpful is because if I square both sides, then this square root squared is going to cancel out. And that is going to give us that distance squared is equal to x squared plus 5 minus 2x quantity squared. And that is going to be a lot easier of a function to find your critical numbers for than just looking at your distance formula. So again, you could, if you wanted to, you could work with just the distance formula and minimize that function, but it is going to be easier to think about minimizing the distance squared. All right, so if I take the derivative, now that I have my function, if I take the derivative, I will get that the derivative is 2x plus, and then the derivative here using the general power rule, 2 times 5 minus 2x, and then raised to the first power, multiply by the derivative of the inside, negative 2. So I want to take that derivative and set it equal to 0 to find out my critical numbers. So the first thing that I would do is maybe multiply by this 2 times this negative 2 to get negative 4 times 5 minus 2x, and then the 2x is equal to 0, and then simplify the negative 4, distribute that to get negative 20 plus 8x, and then the 2x is equal to 0, and then combine like terms to get 10x minus 20 is equal to 0, and then solving that, we get that x is equal to 2. Now, the question was, where is this line closest to the origin? So just saying that x is equal to 2 is not sufficient. What you have to do is you also have to find the y coordinate. So that is where we're going to go back to our constraint. And our constraint was that y is equal to 5 minus 2x. So plugging in this x value of 2, we will get 1. Y is equal to 1. Okay? So the point where we are closest is going to be x is equal to 2, y is equal to 1. And I do want to just mention one thing, that if you were to go through the first or the second derivative test or the first derivative test, you can easily verify that this is truly going to minimize the function. And I just want to talk about that really quickly here. So if you look at the simplified version of the derivative, if I were to take the second derivative here, I would get 10. That would tell us that we are concave up, And if we're concave up by the second derivative test, we clearly have a minimum. So this x is equal to 2. If you just use the second derivative, you can easily verify that it truly does minimize the function. Okay, so our point is 2, 1.